I think now what we want to do is like, we found OPEs last time of like base fields from brackets, right? And also of derivatives of base fields with themselves. Now we'd like to talk about how to find OPEs of like composite fields with themselves or with other composite fields. By composite, I mean like you don't just have a generating field and its derivative, you have it normally order producted with some other stuff. All right, so we had this Heisenberg generator last time, right? We derived its OPE from the bracket. And then we had this like little exercise where we found this kind of like general OPE of DH, well, maybe like an nth derivative and an nth derivative. And what was that OPE? All right, well, it's easy. Like, right, you take m z derivatives and n w derivatives. Notice that that's going to increase the denominator, m plus n, right? So now the denominator is z minus w to the m plus n plus 2. And then each product will give you a successive number. So you'll have 2 times 3 times 4, ending at m plus n plus 1, right? So you have m plus n plus 1 factorial. Don't be like, and the factorial is like kind of a red herring. The factorial comes from the fact that like doing a descending product and ending at 2 is the same thing as doing a descending product and ending at 1. Because anything times 1 is the same thing, right? Like if this had been like a 5th power or something, this wouldn't have been a factorial. It would have been a descending product ending somewhere. And then we need a minus 1 to the m, right? Because the z derivative doesn't have the property that the minus sign from the exponent cancels out with the minus sign from the coefficient. All right, so we have that. Just as helpful or potentially more helpful, I don't know, how do you measure helpfulness? Of this is, so this tells you that dmh sub r. So the dope thing here is that we can read off like exactly what this product is, right? Right, so you know the product's going to be minus 1 to the m plus n plus 1 factorial, but it's only going to be that for a certain thing, right? The product is 0 almost all of the time, right? It's only non-zero at the product that is associated to this pole. So what product is associated to this pole? No, but like which numbered product? M plus n plus 1. So we can like encode that like this. So this product is 0 unless r is equal to m plus n plus 1. No, it is. It's super handy for this, right? Okay, so now that we've got this kind of stuff, we can talk about finding OPEs of composite fields, which is equivalent to finding non-negative products of composite fields, right? Like, in fact, sometimes when you would look at a paper or something of something that has a really large OPE, you wouldn't actually see it as the series. You would just see the positive products enumerated. Okay, so let's say, I don't know, we could do it super generally, but let's not do it generally like to start. Let's find the OPE of HZ and the normally ordered product of, so we want to find that. But notice that this is equivalent to producing a formula for H sub R of, HH, right? It's equivalent to producing that kind of formula, which is dope because look at our important formulas over there. Yeah, the last one, we can use that, right? So let's do that calculation. Let's do maybe I don't know, we're just gonna have to deal with the indices not being consistent everywhere. So now we can do this, right? We can do HR HH will be what? HRH H plus, I mean, this is not super interesting, right? HRH. And then I feel like we should write it out, the thing that's going to go to 0 for one time. Plus the sum as m goes from 1 to r of R choose M, and then H R minus M H, M minus 1 H. All right, so now we can do it, right? So what's this first one? Look, we can use this rule right here. Yeah, so we can use this rule with just M and N equal to 0 in all of these, right? Because that's what we've got. We've got M and N equal to 0. In fact, looking at it, it wouldn't actually be that hard to do it with these general things, but let's just do it like this. So this right here, this HRH is what? Reading this off. It's minus 1 to the 0, right? 0 plus 1 factorial. So all of that's just 1, right? And then delta R, 1, right? But we can see that from this as well, right? Because like, look, this is the first product on the top, right? And everything else is 0. So that means here we get delta R comma 1, the normally ordered product of the vacuum with H, which is just H. Look, and then we get another one right here. And then what do we get for this? So we're going to get some M goes from 1 to R choose M. And then I forgot my normally ordered product things here. And then, no, I don't need normally ordered product things. No, it's right. Because my index, it's my product, choose my index. Yeah, this 1, 2, 3. Yeah, everything else is good. All right, and then we have, what? This is going to be delta R minus M comma 1, right? It's equal to 1 if the two kind of inputs are the same. I use this equation right here with M and N equal to 0. But now let's observe that this thing right here is really just delta M R minus 1. I think that's kind of a nice way of looking at it because that puts it in terms of our index. Because like, look, R minus M is equal to 1 exactly when M is equal to R minus 1 by algebra. Yo. Okay, so now, I mean, like, we could just write the final thing right now, but let's like sort of take it home. And let's observe this. And that is that this sum collapses, right, to a single term. Right? Because every term in this sum is 0 except when M is equal to R minus 1. So that means that we can just like replace this sum with a single term where M is R minus 1. So that's going to be R choose R minus 1, which is R, just by the way. And then vacuum, like I'm going to put vacuum here, right? Just to replace this with something. Like remember, whenever it's just a number, it's really the vacuum. We generally don't write that, but I'll write that here just like to really spell it out. And then this is going to be what? R minus 2H. If R is bigger than or equal to 2, and 0 if R equals 0 or 1. Right? Because like it collapses kind of different ways. So in the end, you get that this is really just 2 delta R comma 1 H. Yeah. Now, like I'd like to point this out. Maybe this might clear everything up. The field associated to the vacuum is just 1. You could expand it in terms of all the products, right? But the only one that's non-zero is the constant term. So that means that if you do the OPE of anything with the vacuum field, you get just what you started with. Or you get 0, right? Because the OPE is equal to the normally ordered product. R comma 1 in the subscript and then H. So like we said before, sometimes you really just want to consider this via the positive products, right? So HR, HH is equal to 2 delta R comma 1 H. All of this comes from, remember that all of the equivalence between non-negative products and OPE comes from this kind of fact, that the OPE of AZ and BW is equal to the 0th product over Z minus W plus the first product over Z minus W squared plus dot, dot, dot. Yeah. So like, look, this tells you the only product that's non-zero is the first product. Because like, look, that's the only pole that we have, Z minus W squared. I just called it typeset.
Okay, R comma 1H.
Lols.
Okay, so that means that when R is 1, which is obviously this one. Okay, that makes sense. I just literally, earlier when I was talking about the notation down here,
I get it.
pronounced it in a weird way, and you were like, yeah, and then you
Yeah, you
affirmed
like,
my misconception.
you emphasized the wrong syllable.
True.
All right, so now this. We should do the OPE of HH with HH. So let's do that. So remember, this is just to like spell it out. This is equivalent to knowing HH sub R HH. It's equivalent to knowing that, right? For all R. Okay. So let's see. We'll do HH R HH is going to be equal to what? So the sum m bigger than or equal to 0 of 1 over m factorial. And then what do we have? So let's be real thorough here, right? So what do we have? We have A, B, C, right? Yeah. Because like, look, we calculated this, right? Yeah. Okay, so let's see. It's the mth derivative of H being normally ordered producted with the m plus rth derivative of H with HH. Right, okay, are we cool with that? That's the first term. Plus the sum as m goes bigger than or equal to 0 of, so B, which is H, sub R minus M minus 1, R minus M minus 1, and then what? And then HM, normally ordered product of HH. So we got something like that, right? So that's 2 delta M plus R comma 1, right? Okay. Which, for what it's worth, is 2 delta M 1 minus R. But we're going to have to be careful because M is only running over 0 and bigger. So that means that this R is automatically only 0 or 1, right? Yeah, so just keep that in mind. And then what is this boy? Yeah, so that is 2 delta M1 H. Okay, so that means from the first sum we get 2 terms, right? Doesn't seem like we get 2 terms from the first sum. A 0th term and a first term, right? First sum, we get the 0th term. So let's see, that's going to be the normally ordered product of H with, oh, I forgot an H over here. This was an H. With 2 delta 0 R minus 1 H. So this is first sum M equals 0, right? Now we need first sum M equals 1. So that's going to give us the derivative of H, normally ordered producted with 2 delta 1 R minus 1. So this is the second, sorry, this is the first sum again, that's how I'm writing that, with M equals 1. How do we know this 0 right here? From this right here, right? So by our argument, remember M is only going bigger than or equal to 0, right? But the only time this side over here is bigger than or equal to 0 is if R is 0 or 1, which corresponds to M being 0 or 1, right? Yeah, so that means we don't need to go to M equals 2. We could have M equals 2 in here, but this is never 2 because this R is positive. Well, non-negative, loosely positive. All right, so we have that. And then let's see, what do we add on to that? Well, notice we just extract the first term, right? Which is M equals 1. We're going to get H R minus 2. Good. Yeah, which is what? 2H. So I can bring the 2 out front. 2H R minus 2H. Now let's split this into cases, right? Okay. Now we're going to have one setup where R is equal to 1. Well, no, let's go down the road. So R equals 0. R equals 1. R equals, I kind of know how far we're going to have to go. R equals 0. R equals 1. R equals 2. R equals 3. Because I can look at this right here. So look at this. So R is positive, right? R is non-negative, right? So if R is non-negative, if it's 0, you have H minus 2H. That's a normally ordered product with a derivative. H minus 2H is a normally ordered product with a derivative, right? Because that's, we had that, that's our kind of fact from last time, that like y u minus n minus 1 v z is 1 over n factorial, then the derivative of v, the derivative of u. That links, remember the positive products from the OPE, the negative products give you the normally ordered product with derivatives. So that's that, right? And then we know R equals 1. Notice that's going to be H minus 1H, which is just normally ordered product HH, right? Then R2 going into this is H0H, which we know is 0 from the formula over there. R equals 3 going into this, H1H, which is something from the formula over there. R bigger than 3, you have H sub something bigger than 1, H, which is 0 from that over there. Okay, so let's write all these down. So R equals 0, who survives? I think only this survives. Like, look, because if R is 0, these don't match, right? R is 0, these don't match, right? This is the only thing that we get. We get 2H minus 2H, which as earlier as this over here, that's 2, and then the derivative of H. Yeah, so you're going to get another term which is exactly the same. Right? That doesn't give you anything yet. Yeah. So you get 4 of these.
That makes sense.
Yeah. Okay, then R equals 1. Notice nothing here. Wait, no, we get something here. We get something here, and we get something here. So here we get 2 normally ordered product of H with H. Here we get 2H minus 1H, which is another normally ordered product, right? So we get 4HH. All right, now R equals 2. 0 here, right? Because like if R is equal to 2, that's not going to match that. R is equal to 2. The 0 here, right? R is equal to 2. 0 here, because we have H0H, which is 0 from that over there. So this is 0. R equals 3. 0 here, 0 here, 2 here, right? Because we get H1H, right? H1H, which is 1 from that over there. But it's multiplied by 2, so we have 2. And then those are the only non-zero ones, right? All right, so let's summarize that. So what? It's going to be 2 over z minus w to the 4th, right? That's this one, right? Then it's going to be plus 4 HH over z minus w squared. That's this one, right? Good, and then it's going to be, I'm going to write this in a weird way. I'm going to write this as 2. No, that's fine. And then 4. Then I'm going to bring the derivative out. Wait. No, I'm going to bring 2 and then bring the derivative out. Because it's commutative, right? The Heisenberg thing is commutative. By what we said earlier, all the free fields commute within the normally ordered product, because this is always going to be a derivative of the vacuum. Yeah. So that means if we take the derivative there, what do we get? We get h prime h plus h prime, But then you can commute them and get 2h prime h, right? Right? Do we feel okay about that? Well, no, we can commute them because they're like free fields. So when you have free fields, the positive products are always just numbers, right? But then you've got a derivative of a number, which is 0. And this is over z minus w. So we've got that, right? Now let's set L equal to 1/2 the normally ordered product with h. And then from this, can we write down the OPE of L? So here you'll get this. You'll get a 1/2 over z minus w to the 4th plus, look, it's going to look like 1 HH, right? Because like you divided by half times half, right? It's 1 HH. But 1 HH is 2L. So you have 2L over z minus w squared plus the derivative of L over z minus w. So you get the Virasoro relations. All right, so now I think this is maybe a good exercise. Okay, so do this for the fermions, but in this case you have to add derivatives in there because you can't smash two phis together. Because again, you can't smash two things of the same type in odd algebras because they'll kill each other, right? So yeah, that means that if we're doing like the kind of most simple extension, you have to do like phi with the normally ordered product of d phi phi, right? And now let's recall this from last time, I believe, that we had a formula which was the mth derivative of phi. We had a formula for this normally ordered product, or for this OPE, right? Which is equivalent to a formula for dm phi sub r dn phi equals some stuff. What did you guys get for that formula? Like, it's essentially this, it's just you're taking the derivative of, you're like starting earlier, right?